So, hi, my name is Kevin Harms. I work in the Argonne Leadership Computing Facility with Yasaman. And as part of the workshop today, I'm going to give you guys like a brief overview of Polaris and how to use it. If you've used Polaris before, some of the introductory things are the same. I'll give some specifics for related to the workshop in the second half. If you've never used Polaris before, then hopefully you'll get a brief overview of what to expect. So first, I'm just going to talk about the system itself. So here is the kind of a representation of a single node configuration. It's a single socket, so there's one AMD CPU. It has 32 cores. I'll give more info about the CPU later. And then the node has four Nvidia A100 GPUs. So generally, we expect the heavy computational code to be running on the GPUs. You can kind of see that we've got quite a bit of capabilities here, 78 teraflops with the four GPUs combined. And then you can see a very high NVLink bandwidth between. So if you want to share data between the GPUs, it's very efficient. Couple things to note. We do have SSDs on the node, but they're not currently user accessible. So that's still a TBD that will eventually be available. And currently right now, Polaris is not using Cassini. It is running what HPE refers to as Slingshot 11. I'm sorry, Slingshot 10. And so you can take, for example, the performance here and it's half. So we're running out 100 gigabit interfaces instead of 200 gigabit interfaces. So eventually we will be upgrading to Cassini in the future. So this will be what to expect when that upgrade is completed. But for now, this is what we have. One last note is you can also see that the node has a fair bit of memory with 500 gigabytes. So I'll just mention a few things, just some details about the CPU itself. So we have 32 cores. Note that we have the Milan CPU, so it's Zen 3. You'll note later that our default configuration has the compiler building for Zen 2. This has to do with some legacy constraint between the Nvidia compilers, and they're not able to deal with the Zen 3 instructions. So right now we have the system configured to build for Zen 2. So just FYI, if you want to get, for some reason, very high CPU performance and you don't need to interact with the GPU, you could load a different module and use Zen 3. We have currently hyperthreading on, so you'll see that it shows us 64 threads. That's kind of the main takeaways for the CPU. Again, just to go through the A100. So the most right column would be the combined four GPUs, but let's just look at a single GPU. So using normal FP64, you can get 9.7 teraflops. If you're able to use the tensor cores and generate tensor code, then you can get 19 teraflops. So if you do matrix instructions, there's a lot more throughput there. And then, of course, if you're using machine learning or other smaller precision or lower precision variables, there's higher performance. And again, the HBM2 on the A100 allows very high memory bandwidth. So memory bandwidth intensive code will best run on the GPU. And let me say a few things about the interconnect. So as I said before, currently we are running Slingshot 10. In the future, we'll upgrade Polaris to Slingshot 11, but that's not something we currently have. So many of the features that I listed here, we do have this Rosetta switch, but these are not currently enabled by the Slingshot 10 NIC, and we'll wait for the Slingshot 11. So our current performance, we have a total injection of about 14 terabytes a second and a bisection around 24 terabytes a second. This is if you're using all groups. And so to get an idea of the network configuration, so we have 10 compute groups. So depending on how your job is allocated, if you're using a few nodes, you'll be in one group. If you use a lot of nodes, it typically will spread out among groups and give you the maximum global bandwidth between your nodes. And so we've got 56 nodes in a single group. Just to cover a little bit about the storage on the system. So we have two main file systems that are shared with our other compute resources. So we have Grand, which is the system we'll be using today. It has a peak performance of 600 gigabytes a second. However, currently this is limited by the number of gateway nodes that we have configured. And so right now we don't have them all configured due to supply chain issues of getting InfiniBand cables. So at some point, we'll be able to drive this to higher bandwidth, but today the performance is going to be lower than what would be achievable. There's a second file system, Eagle, that's identical to Grand, except it has some additional capabilities for Globus sharing. You have to specifically request a project space here if you want to use the Globus sharing capabilities. And like I said, in the future, the gateway nodes will provide plenty of bandwidth, but today we're still limited. Next, we do have our shared home. So if you had been using ALCF systems previously, you'll be using your same home file system that you use on other systems. So when you log in, you'll see all of your previous files. Now I'll move into saying a little bit about how you use the system. So today, everyone has access to this ALCF training if you properly submitted for the workshop. So you can use that. If you have an existing account and you have an existing project, you can go ahead and use that project if you like, but if you don't, you can use ALCF training. To log into the system, you're going to use whatever username that you were allocated by the ALCF and SSH to Polaris. And then you'll use your PIN plus your one-time password to log in. As I said, we have home and then Grand and Eagle. And if you want to use these resources or have other projects, feel free. But here I point us to the path that where we have access to today, which is this LUS Grand Projects ALCF training. People can read and write in this folder, and we'll be sharing this today. Unless you have your own project space, we'll be sharing this. And so try to be good citizens and either don't overwrite other people's files or don't cause problems. And also understand, don't put anything in here that you don't want other people to read, as they will have access. Our system is using the HP Cray programming environment. And so this is based on modules. So when you log into the system, you can start out with module lists, and I'll show you what the current default modules. I have those listed here. And I'll make a couple notes here. By default, like I said, we were using this ROM optimization because that is more compatible with the current Nvidia compilers. When Nvidia supports the Milan instructions, then we can upgrade this. Also, control of the Nvidia Hdfi SDK, we're running a slightly older version, 21.9. We do have another version that you can load if you'd like, if you need a newer stack. And then finally, we have the NVIDIA programming environment as default. So you're going to use NVC, NVC++, or Nvhpc as your compilers. If you would like to use another one, there's a programming environment for GNU as well in the system, or you can use the Cray compilers. Then we also have this option here, which sets some options for the NVIDIA compilers, which tells it which architecture to use. It also enables some of the GPU direct facilities, as well as it sets a flag which tells the compiler that you're trying to build GPU code. So if you compile something that's not GPU code and has no GPU code, it may emit a warning saying like, hey, you used a flag incorrectly. You can just ignore that warning. It's okay. Just currently, we don't have an easy way to disable that warning in a global manner. And if you want to see all modules available, okay, thank you. If you would like to see what all the modules we have, you can do module avail. It'll list, you can page through and see all the different modules available. And then occasionally people will have other modules that you can have, and you have to select those specifically by using module use and put the file path to where the modules are located. All right. So building, as I said, we're using the Cray programming environment. If at any time you want to so it has a wrapper, you're going to use CC uppercase, or FTN for Fortran. And CC uppercase is C++, and CC lowercase is C. If at any time you want to see what it's exactly doing, you can add this cray PE verbose flag, and it'll print out what it's actually issuing as command line. These compilers with the programming Nvidia support CUDA code as well as OpenMP target offload code. Nvhpc is still available, but it's not used by the wrapper. So if you're using this directly, it's still on the system, but you would just call it as Nvhpc. And like I said, we have a GNU environment if you want to switch to that, and then that gives you your classic GCC. In general, if you're looking for a library, for some reason, if you need to construct your, rather than using modules or something, and you need to construct your include or library paths by hand, you can look in opt-Nvidia or opt-Cray or other libraries. All right, so how to run. So I put an example on the right here. Scott has for the hands-on a script that's already written, so you can just use that as a starting place. I'll just go over a few elements here. So with PBS, you can give your flags in the script, and PBS will read those, so you don't have to put them on the command line. But you can also put all of these items on the command line if you wish instead. PBS will tell you how many nodes you got with this variable. If you want to run where you're submitting the job, then you need to put the CD PBSO workdir. Otherwise, you'll be running from a default directory, which is not where you submitted from. So be aware of that. Depending on which behavior you want, it doesn't matter. But if you want to run from where you're submitting, so for example, use a relative path from where you submitted, you'll need to add this. You can load any modules that you don't have loaded by default here, and then use MPI exec to launch your job. I also suggest that it's good sometimes to throw this env command in. So if you wonder like, oh, what was this environment variable set to, you'll find that in your output. On this system, when you launch your job, this launching running of the script runs on the head node of your job. That means you could potentially put some computationally expensive code in here if you wish, like you need to do some analysis before you MPI exec, or after you MPI exec, you want to do something. It's free. This is you're running on your own node, which is different than Cobalt previously. So feel free to go ahead and run things in the script as though running on your own resources. For today, we have a workshop queue. So I printed the queue here. This is, if you use this queue, then you'll be running in the reservation and jobs will run quicker. So I suggest using the workshop queue. And when you submit, PBS will return your job ID. Also note the output and error logs are in the submission directory. And I think currently we have by default an option set in PBS that it generally is syncing the output. So you should see output appear in the logs as the job runs with some delay. Here's some other commands for PBS that you might be interested in. So qstat, you can check the status of the queue. If you just want to know about the job you submitted, you can use -F and put your job ID. You'll get all the details. If your job completed and you want to see what happened, you can use this -X. It will show you information about the job that was completed. So for example, you want to know which nodes that your job ran on or some other setting, you can use qstat -X and give it the job ID. You can, if you want to cancel your job either while it's running or before it runs, you can use qdel. If your job is running, it'll send a kill signal to your job, and then your job will die. Additionally, we're running in the reservation queue today, so we have limited limits set, but normally for production, I suggest checking our documentation. I'll show you that at the end. And there's certain wall time and queue size limits. And so you want to make sure if you're running in the production queue that you set those correctly. Otherwise, your job will not run because it's not able to meet the specifications required. PBS also allows you to select some more specifics about, like, if you want to run on a very specific node, you can set that. Obviously, the more specific you are about where you want to run, the longer your job is going to take to run. But you can do that. And then also, this is a future option. You'll see this in some of the examples. System equal Polaris. Currently, you can drop this. It won't matter. But if ever in the future we have a combined scheduler that allows scheduling on multiple systems, this tells you which system you're targeting. And currently, we don't have anything. The nodes are set to exclusive use. So using NCPUs or NGPUs generally doesn't do too much because you already have the full availability of the resources of the node. So you can just set these things in MPI exec to try to what you want. You have all the cores and you have all of the GPUs available whenever you run your job. If you are coming from an ALCF background and have been running on our previous systems, Theta or Cooley, we were using a different scheduler called Cobalt. And of course, it had a PBS-like syntax. So it's similar, but of course, slightly different. If you have an old script and you want to reuse that on Polaris, you can use this qsub to PBS command, and it will translate your old script to your new script with the new syntax. It's not perfect, but it can give you a jumping off point if you just want to port your commands from Cobalt over to Polaris. And if you want to know the status of nodes, there's this PBS nodes command, various options. It can tell you which nodes are down, what nodes are available, what nodes are occupied, if you want to look at this current state of the system. So running MPI applications. So we use the HP PAL service for launching. And so it uses an MPI exec wrapper around what they call PALs run. The MPI exec command is very close to what you would get from mpitch, but there are some slight differences in the arguments. So if you're looking for a specific argument, I suggest doing a man MPI exec or MPI exec help and looking at the specifics because there could be some slight differences. Again, Scott has examples of these, but some key parameters are setting the CPU bind if you want to try to bind threads to cores, and then setting the depth for how many cores each rank is going to be allocated. Then if you're interested in tuning your MPI, HP has many environment variables available in Cray MPI. So if you do man MPI intro, there is a long list of things. It will tell you which things are set by default, but you can affect the rank map placement. You can affect how the GPU is used in conjunction with MPI, so on and so forth. So if you're looking for something specific, I suggest checking the man pages there. Next, we do have Python provided by the Cray PE. And so these are designed to work. So MPI for Pi is designed to work with the Cray's MPI libraries. So if you load the Cray Python module, so if you do module avail and then search for Python, you can load this module. It has NumPy, SciPy, Pandas already built in, as well as an MPI for Pi designed to run on the system. So if you want to test any Python code, you can try this Cray Python. Finally, we do have the debuggers available. So GDB for HPC is a variation on GDB that does parallel stepping of your job. This is good if you need to debug something when running like with multiple ranks. Currently, stat has some issues, so I don't recommend trying that. And then if you want to use, like if you want to debug something on the GPU, you can use CUDA GDB. Then if you want to profile a whole system, like you want to run a job and see how much time is used in MPI, how much time is used in GPUs, other things, like very general scale, you can use CrayPat. And so this is what you want to, if you're doing some whole system profiling. If you want to just debug, like, or I'm sorry, profile your GPU code, you can use NVIDIA's Insight. And as I said before, if you want the details on Polaris, you can go here. Anytime you need help, you can always email our support address. And of course, our documentation. I strongly suggest looking at the documentation. It's currently evolving. We've added a lot more documentation since Polaris has started. And so we are continually adding to that. And of course, if you feel things are missing, we now have it hosted on GitHub, so you can open an issue or send us a pull request to help improve our documentation. That's my kind of brief overview. Of course, Scott in the hands-on will go into details of the specifics of running the examples, but does anyone have any kind of general Polaris questions right now?
Thank you, Scott. There was one question which I think you believe you answered in the next slide, that they were asking about the A100, if it's 80 gigabytes or 40, which it was 40 in your.
Yes, yeah, we haven't the older 40 gigabyte A100s.
And I think there is one that is asking about H5 Pi, so the Python version of, I guess, HDF5.
Yeah, HPE does have provides a HDF5 build. I don't know if their CrayPython has the H5 Pi interface built into it. I'd have to check that. But today we will not be using HPE's build. We'll be using Scott's build as its newer release. So I'll let him go into the details of the H5 things we have for the workshop.
Yeah, I think at this time we have a Scott. So if there are no more questions with respect to the Polaris, and you can always use the Slack space, and I did paste the links to join at the very beginning of this chat. If you don't have it, just send the chat again and I will provide that to you.
Kevin had a question. So what's the difference between the NVIDIA module and the Nvhpc? Is it, because I use that to compile everything?
Yeah, so the NVIDIA, so there's a programming, there's a module called NVIDIA, and then there's a module called Nvhpc. They're essentially the same. Nvhpc is going to be the module going forward. So at some point, the NVIDIA module will be dropped, but currently there should be functionally equivalent.
Okay. Okay, my name is Scott Breitenfeld, and I'll be giving the talk on HDF5, discussing parallel IO and then performance tuning. And I'm here with Jordan from also the HDF group, who works as a colleague of mine and works on a lot on the parallel aspects. So he's here to answer questions if you have in the chat, or if you want to interrupt me, that's fine too, as I go through the talk. So basic an outline, I'll give an overview of parallel HDF5. Actually, I won't go into the details of parallel HDF5. I assume that you already have some experience with parallel HDF5, and this talk's going to be mostly focused on how to get better performance out of your already HDF5 parallel code, or if you want an introduction into using newer features that we've been introducing to get better performance, especially at exascale, then that's what this talk is really main to what's going to focus on. So just to get out the resources, their HDF5 homepage is listed here. We also have where you can report issues or bugs or new features on our Jira. And we also have GitHub issues. So you can either do it in the Jira or on our HDF5 issues on GitHub. We also have documentation. We have two sets of documentation right now. One where it's a little older and it was kind of manually made, And now we're moving into Doxygen. So we're revamping all our documentation to use Doxygen, and you'll see a link in the documentation page to that new Doxygen generated documentation. So if you want to look at that, that's probably the most up-to-date going forward. The repo, there's a link here on GitHub. You can download it with all the different versions. We also have if you want to look at some parallel knowledge base, I have a link here for past questions and answers, best practices about parallel using HDF5 in parallel. If you have questions, you can ask them on the forum. I have a link here in the HDF group. You can also send a help email to the help desk at HDF5. And we also hold a weekly HDF clinic. So it's usually only 30 minutes each Tuesday. And you can ask, we have people at HDF5 man the desk at the doctor. So if you want to just figure out, ask a question there, you can do that as well. You just have to register. And finally, the latest releases you can download them all from this link. And currently we have 1.8, 1.10, 1.12, 1.13. But just a heads up, we do plan probably next year to phase out 1.8 and 1.12 and just go forward with 1.10. And then what the next release will be 1.14. And for this talk, we will be using 1.13 for various reasons. First, it's new, and two, there's a lot of new features in it that will support, especially exascale. So I'm going to discuss now just general parallel HDF5 best practices affecting parallel performance. First, we have to discuss vol, which is a new feature starting at 1.12, and that's basically an abstract layer within HDF5. And it basically redirects some IO operations into a vol connector, which I'll show next slide. And then immediately it either invokes an API routine within the vol or then does something and then returns back to the native HDF5. So the vol connectors essentially can implement storage for HDF5 objects, and they can also work with methods that work on those objects, such as you can create data sets, read, write, selections, and querying metadata and closing. You're able to use vols pretty transparently. You can load them as a dynamically loaded shared library, and you don't have to modify any of your application source. And you'll see that in the demo. We're going to demo one of the vol connectors today. You can also stack vol connectors. So you can do a pass-through vol, which I'll discuss, in the terminal connector. And then that way you can do various things with it using each vol connector. So as a high level, what the library architecture looks like, this is 1.12 on. So you have the API and language bindings. Then you have the vol layer, which is the virtual object layer. Then you have the core library, and in that you have the pass-through vols. Those are vols that do something to an object and then go to a terminal connector in the end. So right now we have an async vol where you can do async IO. We have a cache vol that manages, if you have, say, a burst buffer, it can manage the memory buffer between the burst buffer and, say, persistent memory or persistent to disk. We also have a log-based vol. This is one that we'll discuss and we'll demo here because it's developed at A&L. And we'll talk a little bit about that as the talk goes on. And then finally, you have terminal connectors. These are the vol connectors that actually persist the data to disk. One is the Deos vol connector, which uses the Deos file system, which is at A&L. So you can write to the Deos system using that vol connector. We also have an Audios connector that writes in that format. And then we have the VFDs, and we have the POSIX, you have the Mpio driver, and then you have various cloud solutions if you're interested in that. And we'll discuss a new VFD coming online later in the talk. So just a reminder that the parallel HDF5 has various implementation layers. Of course, you have the application running on the compute nodes, and then at one layer have the HDF5 library, and the HDF5 library for parallel IO depends on the Mpio library. And then then the Mpio library talks to the file on the actual parallel file system. And so you have to consider that you have the interconnect network between the Mpio driver and the IO servers themselves. So this the file is usually laid out on a parallel file system in a striped kind of manner. So there's really three layers you have to consider tuning. You have the HDF5 library itself, the MPI library if you want to tune that, and then you also have the parallel file system if you want to tune that. When you first start off writing a parallel program, the first thing you want to consider is whether you should create all your metadata, such stuff like creating groups or data sets, using all the ranks, or should you just create those with one rank? So you open the file, create all your data sets that you plan to create during the simulation, close the file, and then reopen it with all the ranks to do the actual raw data writes. And there is some advantage that we've seen in the past of having just one process create all the objects compared to having all the ranks create all the objects. So it's not a huge difference, 1 to 5 seconds, but if it's not inconvenient to usually create on one process, that's what we suggest doing. There is a issue with some of the newer features that we've developed that you might not be able to do it this way if you use some of those newer features, and I'll discuss that a little later in the talk. One thing to note, if you do create using a single process, some of the data structures in the HDF5 library, that the allocation of those objects are affected by what mode you create them in, whether you create them in sequential mode or a parallel case. So in the sequential mode, when you allocate, so for example, chunks, they are allocated incrementally. So when the data is written to the chunk for the first time, where if you create that data set in parallel, then the chunks are always allocated when the data set itself is created. So one issue that we found in the past is that we were creating the data sets with one rank and then opening them with the others. And what we found that there's a certain fill value that you can set, that if you don't set it, then when you created that data set in serial, it wouldn't be allocated, but then when you reopened it in parallel, the HDF5 library saw that it wasn't allocated yet, allocated it, and then it filled all those values with a fill value. So, and that really, there's no reason to really do that. So you can see the difference. The bars are what it was with having those fill values written, and then the dotted lines are turning off those fill values. So what we recommend, unless you need to know what values you haven't written yet, and which is usually more on the experimental side where they have sensors, and they might not have a value that they've received, they want to know that. But usually you should always just set the fill time to never. And you'll see that in all the demo programs that for one of the optimizations is just to always set that to never. Another thing we'll talk about is various third-party libraries, and we are actively involved in CGNS, which is a computational fluid dynamics general notation system. It's basically an effort to standardize CFD input, so it writes grids and connectivity boundary conditions and other information in a standardized manner that the visualization and other software can read it without interpreting it. And it has two parts. It has the format for the standard, and it has the software that reads the standards. And so this was used a lot to help tune both the CGNS itself and using HDF5 and tuning the library itself. And you'll see that we've added some features that we needed to add for HDF5 to get good performance out of it. It's also useful for if you're using a third party, we often benchmark those third party applications such as CGNS and Netcdf with various versions. For example, here we've benchmarked CGNS for all versions of HDF5 up to develop, and we kind of monitor the performance for each version using CGNS. And for the parallel, we don't see much of a difference. So that's just one thing to keep in mind, that we've have tuned a lot of these third-party applications such as Netcdf and CGNS if you decide to use those instead of, if you can, instead of making your own HDF5 output. So here's another example of where we discovered something in the library that CGNS was doing that we had to account for, and that was if when you have a standardized format, sometimes you would just have all the processors, you write the data just because you need that data set there to meet the standard. And then what they were doing in CGNS was having all the ranks read that essentially data set, all the data sets. So they're all reading the same data. And what we did for CGNS then was we added in 110 that if we saw that all the processors were reading or writing all the same data, and we set a limit to if the data set was less than 2 gigabytes, then we just had the lowest process read the data and then broadcast the data to all the other ranks instead of having all the ranks read the same data. And you can see the improvements. So the solid line here is the all reading it, and then the dotted line is just having one process read the data and send it out to the other ranks. You can get this same effect by using compact storage, and because this uses the same algorithm. And in CGNS, we later converted a lot of the data sets to compact storage, so we didn't have to worry about this feature in HDF5. This also helped the scaling of CGNS itself. So the solid line here is with the baseline. This is the original. Then we had tried to read the data from process 0 and then broadcast it, and that's within the application itself. And this took it down from a day to an hour. And then we switched to CGNS to use compact storage, and that got it down to minutes, and which also got it very close to a file per process time. And you can see that because we're doing essentially a broadcast, and this is just how a MPI broadcast performs on the system. So it follows that trend, which we expect. Another application we've worked with is E3SM, and this is a Earth's air system model, and it uses two levels of software for its I/O. They have this Scorpio I/O, which is basically a high-level parallel library for structured grids, and then Scorpio used Netcdf, which then uses HDF5. And one issue that we had with Netcdf is if you use the high-level libraries such as dimension scales, those aren't parallel. So when you use the high-level libraries, all the ranks are just gonna do the same operation. And you can kind of see it's not a big difference between having all the ranks call those high-level libraries. For this case, it was the dimension scale H5DS by all the ranks, and then just by one of the ranks. We also had an issue with E3SM in that it writes hundreds of variables, which basically has small portions. It essentially creates really small data sets, and it writes all those variables. So what we found was that for that case, we wanted to investigate maybe not using Netcdf and bypassing it and just do an HDF5 only implementation. So here we discuss how we changed from using Netcdf to HDF5. So essentially, we again have rank 0 initialize all the metadata in the HDF5 file. Then we use the HDF5 hyperslabs to merge the 2D and 3D requests, all these smaller ones, into a single data space. And then we changed the memory space and sorted them, aligned them, and then created a new data space. And then we also have a new feature that we're introducing in 113.3, which should be the next release of the 113 series, and of course it'll be in 114, is that if you have multiple data sets that you're creating, so if you have a vector of 3 components, normally in HDF5 you'd have to create a data set for each of those components and then write those data sets. With the multi-data set, now we're introducing an API that you can write all 3 data sets using one call, and that should optimize underneath that. Instead of having 3 writes, it should just have 1 write. So that should help your performance. If you have a lot of data sets, you can use the multi-data set to get a better implementation. And so we monitored the performance on Cori, and we were able to get the write performance for the data only comparable to what you would get with pNetCDF write performance. Another option that we've found very useful is in HDF5 is to do the H5P set alignment. This controls basically the alignment of the file objects in the address, objects on addresses in the file. So for example, we looked at the effects of this is for the Vpic application, where we monitored it for each quarter, and then we switched on the alignment. This was on Summit, which we've seen, which uses GPFS, and you can see the improvement in the write bandwidth for each case. This is a blue compared to what it was before. Now, one issue that you can have if you do align all your objects, and you can set a minimum threshold for that. But for example, if you're chunking your data set, then each of those chunks are going to be aligned. So that could really increase. And if you have those chunks not as a multiple of that alignment, then you could have really start to increase the size of your file. For this case, we're using contiguous data sets. So as the number of processes increased, you can see that the file size didn't increase as you increased the number. So the file size was very minimal impact with a set alignment for this case. But that's just something to be aware of. If you are using H5P set alignment, that it could blow up the size of your files needlessly. In general, you want to, and I'll show this as some of the examples, you want to issue the largest IO request possible. You also want to avoid data type conversion if you plan to use, for example, collective, because that will break it. You also might pay a penalty if you do a data space conversion. So if you write a one-dimensional buffer in memory to a two-dimensional array in the file, that you might get a penalty for that. And then you can monitor whether that your writes or reads were collective or independent by calling this call here, which tells you what it was, what it actually used, and then then you can find out the cause of it by calling this MPI if it's not what you expected. In general, you can use contiguous data storage if you don't have if you don't plan to extend the data set, or if you don't have compression. You can use compact storage, which is often overlooked if you have less or small data sets, 64K. The nice thing about it is it becomes part of the HDF5 internal metadata. So if you use, for example, if you contiguous storage, it's going to go right to disk, whereas, and if you're writing a lot of them, then that could be problematic. So if you use compact storage, they won't get written to disk until the internal metadata gets written to disk. So it's stored in cache. So this can help you improve if you have a lot of small data sets. If you use compact storage, that should help your performance. You can also avoid duplication. Just remember that you can add links within your HDF5 file, so you don't have to duplicate data that doesn't change during your simulation. You can just add links to it. You'll also have a virtual data set that you can make up a data set that is composed of other data sets, parts of other data sets. I talked about that at the other talk. So finally, you can do chunk storage. So chunking is required, as I said, when you're planning to extend your data set or when you're doing compression. And we do support now parallel compression. And just keep in mind that, and this can hurt your performance, that IO is always performed on a whole chunk. So we don't have partial chunk reads, and all the chunks have to be the same size. So if you do that, you might want to look into chunk caching and how it works. And I've included a link here. And basically, you have to really consider when you do chunk your data as how often you're going to access that data. So you can get good chunking on write, but then when you want to read it back, maybe in a different order, then that their chunking might not be as efficient for reading as it was in writing. And then there's no best answer. We get this question a lot of what's the best chunk size. And it's really a trial and error right now, whether to use the best, what the chunk size should be for your application. And this is especially important for compression because compression is performed on a chunk by chunk basis. So if you use really small chunks, then you're not going to probably get that great of compression. Whereas if you use very large chunks, you might get better compression, but you might not get better performance because if you have large chunks, then you would do a partial read of a chunk. It's going to read in the whole chunk, decompress the chunk, and then write the whole chunk, not just part of it. So when you do partial chunk IO and it's going to read in whole chunks, then all that compression is going to happen on the chunk itself, which could hurt your performance. So something to keep in mind for chunk storage. Another issue that we had with CGNS was what we call a read storm. So basically, a read storm occurs when you have all the ranks independently competing for the same metadata. And you can see the effect of it here. So this is what the time to read. So this is before we have collected metadata, which I'll discuss a little later. And the red line, sorry, is with before the collective, and then this is with the collective, and this is a log plot. So it's pretty impractical once you get to the large number of processors without this mode. So this is something we added to HDF5 to get better read performance. Basically, as you know, for metadata write operations, these are all required to be collective, and you must do this in the correct order. So, for example, if you have rank 0 creates dataset 1, you can't have the other rank create dataset 2. They both have to be involved in this dataset creation. The read operations are not required to be collective, so you can open a dataset with one rank and another dataset with another rank. Or you can have all the ranks open up dataset 1, dataset 2. The problem is that HDF5 treated all these independent reads operations, and if you have a very large MPI job, then all the processors are going to want to open all the data sets that already exist in a file. So when you call, for example, HDF5 dopen, all the ranks are going to read the same metadata to get the data set and the metadata of the data set itself. So that's if the metadata is not cached. Then if you don't set the metadata cache large enough, for example, then it's going to have to go to the disk. So you have all the ranks going to disk to read that data. So this was happening in CGNS, and we termed that the read storm. So what we introduced in HDF5 is these new APIs, these H5P set collective metadata writes, H5P set all collective metadata operations. And this is a property you can set on the file itself. So if you set in a file, then all the read operations will be required to be collective, metadata read operations, sorry. And you can set it also on individual properties, such as the data sets. If set, so the rank 0 will issue the read for the metadata and then just broadcast it to the others. And these two are also in the demo codes that we'll have, the workshop. And you can see the effect of it. Another case that we've looked in the past is we work with the Parthenon application team. And what they do is they create two HDF5 files. These are HDF and PHDF5, and then they couple that with XDMF for visualization. So what we did was study the influence of the IO tuning parameters that they were using. And for this, we just use an example that they have as a benchmark. So for the first case, and this is on GPFS, we just used their defaults that they were using, and that is here in the first column. So this is the two files, the P and the R in different colors. The second case was they were setting an allocation time, so they allocate early. So that means when you create the data set, it also allocates the data set. And then they also, as I mentioned before, they set the fill time to never. And that's case 2, and it doesn't seem to have much of an effect. They then did the collective metadata write, the collective metadata operations, which I mentioned in the previous slides, and that didn't seem to have much effects either. They then they changed the metadata block size to 16 megabytes, and that seemed to improve the performance on GPFS. And then they set the alignments, which also didn't seem, surprisingly, usually this is a pretty good performance boost on GPFS, but this didn't seem for this case to have much impact. And then they also tweaked the MPI layer with various optimizations, and you can see that it didn't have much effect on GPFS. Now, if we go over to Lustre, we see a lot of difference between the two. So here we did the same thing. We first ran with the defaults that they use in their application. You can see the effect of that. Then you have the set allocation time and the fill time, which brought down the time a little bit. The big change, though, was the collective metadata and collective metadata operations, which really had an impact on especially the larger file, which is the R file. And then once they were setting the metadata block size, actually hurt the performance a little bit. The set alignment didn't have much effect on it, but then tuning the MPI info, which they had hard coded for in the code itself, really hurt performance. So if they would have stopped at optimizing at this level, they would have got better performance than trying to optimize for this. So this kind of just shows you that you just can't take all, you kind of have to tune per system, for example, Lustre or GPFS, and then you might not want to throw all the bells and whistles at the case, but kind of do it on a case-by-case basis. And later in talk, I'll show you a code that kind of goes through all these different cases that you can explore. And I ran that code on Polaris, and we can see the effects of that. So just to show you how to set hints for the MPIO layer, you can use this FAPL on MPIO, and you pass it the MPI info parameter. So tweaking it. So there's an example of how you would do that. If you want to set a tuning hint for the MPIO layer, you can do it using this code here. This is what they were doing in Parthenon. So before I go on, is there any questions I should answer? Or am I good to go?
No question. About, I think you talked about a few options. I was wondering about the effect of meta block size. There's the H5P set meta block size option.
Yes. Sorry, what? There, you want to know about it, or?
Yeah, if it had an interaction with the IO that you had talked about, or with H5P alignment, set alignment.
The block size, I mean, in general, or sorry, I don't understand the question.
Well, okay, so we set H5P set meta block size to say the same as the alignment size. How would that interact with alignment? Would that help, or would that?
There is a, well, I'll discuss that in this program here that we do. You can modify that and then modify this set alignment, and you can kind of see what performance issue you would have with that. So I'll kind of discuss that in this part.
Okay, thank you.
Mhm.
One other question then. What is the largest chunk size at the moment that's supported by HDF5?
I think is it 2 gigabytes, Jordan, or is it 4? I think it's.
Yeah, it would be, we store them in signed 32-bit values. So at the moment, I believe it's 2 gigabyte chunks. We're looking at possibly expanding that in the future since it's been an issue.
Got it, thank you.
Hey, Scott. So on you mentioned for 1.13, you can write multiple data sets simultaneously. Do you have any examples, or do I need to change anything in my code, or how would I enable that? Sorry if you covered this and I just missed it.
No, it hasn't been released yet, and it's not even in 1.13 yet. It's in a feature branch, so we're still working on we actually, if you do have a test case, that would be useful for us because you can just try it. But yeah, you'd have to change your code to use those new APIs. There's 2 new APIs for reading and writing.
Okay. Yeah, because we basically end up, we write our 3D data as large contiguous buffers over, so it's a finite element code over chunk of elements, and then we'll have multiple variables, and it just seems like this would be a nice case where I could write all variables at once into different data sets. But so
Right.
yeah,
Yeah, you
awesome.
can do
Okay,
that. I think the only limitation right now is it can't do collective. Well, you're doing independent or collective. You're not doing type convert. If it can't do type conversion.
That's fine. We do all the type processing into either single or double precision floating points and everything beforehand, and then just write it all to disk.
Yeah, it should work fine then.
Okay, awesome. Thank you.
So going on to the simple problem. So this is just writing a 2D array variables over time. So this is common for an application. So you have all your ranks and it's arranged in some kind of process grid. Then you have your time step. Then you have your count. This is a number of data sets you might have. So what you do is you create the array, the size of it, depending if you're doing strong or weak coupling, for example. And then you would just write the array to or from the HDF5 file. So what you have to consider, though, is how you should write that data. Should it be a 2D, 3D, 4D data sets? Do you know the extents ahead of time? How do you want to order those dimensions? And do you want to how do you want to arrange it in groups? You also want to consider how the data is written itself and how you're going to read. Are you going to read the data in the same manner? You want to discuss, look at the storage layouts. So, example, how many physical files do you want? Are you going to plan on using contiguous or chunked? And if you plan to use compression, and then what's the underlying file system and how it's going to affect the performance, and then finally whether you should use collective or independent I/O. So there's two goals. You can have two goals really for doing HDF5 performance. One, if you're, for example, if you're doing CGNS where you have to conform to a certain standards, so you have to have a certain number of data sets, you have to have them created. So there you may be willing to sacrifice some performance for a more self-describing and standard compliant file format. The other one is you just want to do the fastest I/O possible. Maybe if you're doing checkpointing. So in that case, you probably want to minimize the extraneous metadata that you're not using, and then write the largest blocks possible. And if you, the kind of takeaway from this talk is there's a lot of properties that you can use to tune your code. And if you look at the H5P, which is the property list, there's a lot of them, 180 of them, and they basically control the properties of the objects themselves. So if for example, if it's chunked, that gets actually persisted to as part of the disk, as part of the file. Then you have the kind of the in-flight behavior. So that would be, for example, if you're doing independent or collective. But if you look at the file, it's not going to know whether you wrote that independent or collective. It's just going to see the data itself. So that's what we call in-flight. And if you look at those, there are about 100 functions that handle that type of in-flight behavior. And if you look at APIs, a lot of those are H5P defaults. And what we see a lot of users that start in parallel just leave those H5P defaults as that. But you really have to understand what that means, because that can really hurt your performance if you just leave those as H5P defaults. So we want to kind of explore the effects of using some of those H5P defaults. And so we've developed a code called Htf50 Io Test. And basically, it kind of answers the questions of how to do many 2D data sets. Do you want to write them into 3D data sets or 4D data sets? It also explores chunking, data alignment, metadata block sizes, and whether you do collective I/O. So this is a code you can download and try running. And I ran this on Polaris. So just example of what it goes through. This is a parameter space that it cycles through. So if you look on one ray, it does the slowest dimension. So this is the dimension that you want to write. Then it will do the step and array. I'll describe that, what that is in the next slide. Whether you're doing contiguous or chunked, here you have the initialization of the fill values, whether you do true or false, or sorry, if you fill the values or don't fill the values. The next is the alignment that you can set. The next is the metadata block size you can control. You can also control which version of the library is you use. So you can either use the earliest or the latest version. And then the outermost ring is whether you do an individual collective. So if you look along array, those are each parameter space that we explore with this code. For example, if you want to do step-based IO pattern, so if you have your time step 1, time step 2, you have your 5 variables in this case, you can just write a group and then write those 5 variables in the 2D array. Then the other option is if you combine those, so you have step 1, step 2, you write all 5 variables in a 3D array. And finally, if you have, if you know for example, the number of time steps you plan to use, you can just combine them all and write in one big array of 4 dimensions. So this is one option that you have for storing your data. Another option is array-based. So instead you base it on the variables themselves, and each variable then has the time steps of each array. You can combine those into those variables and just combine the time steps, and then you can combine all the variables into a 4-dimensional array. So this is what it means by array and step. So here I ran the case on Polaris with 8,000 ranks, and I reordered those parameter space from the best performance. This is the total time it took to run that code compared to the worst performance here. So the best had, so you can see that this was the rank 4, which kind of makes sense because it's doing very large writes. And you can see that it kind of trends the rank 2, which would have a lot more writes to disk than the rank 4. So you can kind of expect that you get worse performance. It also did the time arrangement of the data. It used contiguous data sets. It never filled the value. It said, don't write a fill value. We used the default alignment in HDF5. It didn't, for this case, I didn't study the metadata, but it's the previous question. You can turn that on and then run it and then play with the different metadata sizes. I also used earliest and latest. You can see that the earliest performed better. And then for this case, collective performed better than independent. So it kind of shows you that if you choose wrong, you can get very bad performance compared to this is a log scale. So you can definitely hurt or help your performance, IO performance, by just choosing the right IO pattern. And this kind of gives you a way to do that. So let's go on to the log baseball. So this is a way to mitigate some of the performance variability you saw in the previous graph. Essentially, it writes data contiguously in the file, like time logs. So for example, if you have a variable 1 and a variable 2, and you've divided that up among the ranks, normally HDF5 and a lot of applications do this, is you'll have process 0 write its part of the data set of the first, and then right after that, you'll have the second rank, and then the third rank also write one after the other. Now what the log based vol does is it just writes, so P0 will write all its data of variable 1 and variable 2 contiguously, then rank 2 will write all its data contiguously, and then so on. So this is what the log based vol does, and we'll have a demo of using the log based vol in the hands-on. So this is an example of using the log based vol with that program that I showed. So this is on Polaris, the same problem, 8,000 cores. And this is comparison of the log based vol to the native vol. So in this case, I didn't reorder them. So this is just the case of the parameter space that was cycled through. So you can see the yellow curve is what the log based vol. So you can see it kind of eliminates some of the peaks. I think some of this was I was running into the hard limit on this file system, so I had to delete some of the files as it went on. But you can see the performance improvement that the log based vol helps compared to the native vol. So that's it kind of minimizes, even if you chose poorly the wrong layout, it kind of minimizes that impact if you use the log based vol. So just to mention the data locations in the file. So the write pattern can affect the performance, as you see. We did this for the hack application at A&L. So as I mentioned, the one, it had 9 variables, and we were writing it, as I mentioned, each rank was writing one after the other. And then what the Mpio output that hack uses, and you can also get with this compound data type, is that you can interleave the data. So this is kind of what the log baseball is doing. So what impact that has on the performance itself. So you can see that if you have your 9 variables, the Mpio access patterns writes it basically contiguously, which is good for the file system. So it would write 0 would write all its data, and then in a different offset, rank 1 would write at another all its data. If you do the mixing of those two, then of course you have rank 0 writes its data, and then it's going to have to skip and write its variable 2 and all the other variables up to 9. So you have this offset, and this can hurt your performance. And we did analysis of that. And what we found is that we could get it to be better with compounds, using compound types. And this is kind of what the demo is geared towards. So it kind of compares, for example, if you had 9 data sets and you're writing those 9 data sets individually, compared to just doing a compound type and just writing all the data sets at once. And that's what the demo is going to show. So you can kind of see what the effect of collective versus independent is. So sometimes you get better write speed. So here you can see that the MPI write at call, the actual write call, let me see, make sure, yeah, that it spends a lot of time for MPI only in the MPI write at call, whereas if you're using HDF5, it also spends the same amount of time in the MPI write call. So what we found is, well, why was MPI IO only without HDF5 still faster than HDF5? And what we found is what the offset of the metadata at the beginning of the file could throw it off. So what you have to consider, which also is a advantage using H5P set alignment, is you can align that data so that the metadata at the beginning of the file doesn't throw off the alignment of all the other writes in the file. So that's another advantage of setting the alignment in the file itself. So we were able to get the same performance as the HDF5 with HDF5 as the just MPI by just setting that alignment, and then also using compound data sets. And you can see more details about this study. This I kind of glossed over because it was a very long study of how the effects of MPIO patterns can affect performance of HDF5. So I'll just skip over the summary. So I'll just go on to some of the performance. Let's see. Can you remind me how much time do I have for this?
I think we're doing fine on time.
Okay. All right. So we have a new feature that we're working on called subfiling. So it's basically a compromise between a file per process and a single shared file. So you'll have multiple files organized as a RAID 0 implementation. So you configure both the stripe depth and the stripe set size. The default for the number of stripe sets is 1 file per node, and the default for the stripe depth is 32 megabytes. And we have 1 metadata file which is I guess we don't have this anymore. It's a little older. We kind of changed this, but the metadata now is all in the subfiles. So some of the benefits of using it is you can get better IO out of your subsystem. So and it reduces some of the complexity of file per process. So instead of having, all a file per 100,000 ranks, you would have them node basis. You can also have more than one subfile per node, so that would increase the number of files you've had, but it still would be less than a file per process. And you can reduce the lock and contention that you sometimes see with as you increase the number of ranks over a single shared file. So for subfiling, and we'll demo this in the hands-on. So it has two components. You have the metadata, so it's written as regular HDF5. So the final implementation, as I mentioned, has the metadata embedded within the file itself. You have the raw data, which is split over in a RAID 0 type file. And it's a number of individual files that are managed by an IO connector. So you have, or IO concentrator. So you have, for example, on a node, you have the IO concentrator. Then you have an option if you have node local storage, you can write it to the storage that is local to the node, or you can have it just go to the parallel file system and write the subfiles that way. So the IO concentrators are implemented as independent threads that are attached to the normal HDF5. It also uses MPI to communicate between the HDF5 processes and the IO concentrator. And so because of that, you have your application, if you're using just MPI init, it has to be changed to MPI init thread. And we'll see an
It's
example.
also probably worth mentioning that subfiling also requires MPI thread multiple for its threading support, which is pretty good, pretty well supported these days on systems. But I know you have to, I think, set an environment variable for impitch at least to get that level of support.
Right, some of the older systems and older implementations, you have to set that to, so it's always good if you set that to check that you actually get that support before, and it's in the example, so you'll see that in the subfiling example of how to check for that. So to run subfiling, then you can just set the file access property list. So instead of calling the MPIO driver, you would create your file access. You would then call the FAPL for subfiling, and then for now, we're just passing this null. This is a struct of way to organize or pass arguments to the subfiling as parameters. And then you would just simply open it as you would before using that FAPL. So it's not much change in your code itself. Then you can control various options in subfiling through either you can pass it through the parameters in the FAPL, or you can set environment variables. So some of the important ones to set is the IO count, IOC count per node. So that's the number of IO concentrators per node. So that's how many files, subfiles per node. Then the stripe size. This is basically the maximum contiguous blocks of data that can be written to as a single IO concentrator before moving on to the next IO concentrator. So this is, and then you have the number of threads that you can use for the IO concentrators. And this is currently set as 4 pool threads in the background. So you can impact, so for these cases, when I ran on Polaris, I used the 32 threads per node. So I still had for the hyperthreading that the IOCs could use those other hyperthreads without probably, I didn't do a study, but I don't think it would affect the performance of the actual computation if you use more than 4 pool threads. So it should run, if you're not overscribing the threads, it shouldn't have a large impact. So I ran IOR on Polaris. So this is, for this case, I just used all the defaults for subfiling. So I just used one node, one subfile per node. And I used a stripe size that matches the Lustre stripes count. And if you use what we found for subfiling, we're still kind of investigating, but we found that if you set H5P set alignment to a certain value, then we get the best performance out of subfiling if you also set the IO strip size to that same size. And I did that, and here I compared for IOR the write bandwidth. So purple is using independent with IOR, green is collective, and then the blue is with subfiling. And you can see the improvement. And we've noticed a trend that you won't see much of a lot of difference at the lower number of ranks, but you really start to see it as you start to increase the number of ranks. You should see a larger difference between just using regular HDF5. Another option for using for improving your performance is using asynchronous IO, and basically, as kind of as obvious, is that you have your compute. You have normally when you do a synchronized, you have your compute, you have your output, and then you just do this in a line. If you with async, you do your computation, then you do your IO, and you do your IO while you're still and then go on to the next compute stage. And so you can kind of overlap your IO with your compute. There's two options with, so this is with the asynchronous vol, which I have linked in the next couple slides. So you can do implicit, so you don't have to change your code, but in general, I don't think you'll get as good performance as if you do it in explicit async. So you have to change your code a little bit to synchronize or to arrange for your event stack, which I'll discuss in the next slide, how to do explicit. So basically it's implemented as a pass-through. So when the actual file will just be a standard HDF5. So it will, the async vol will capture the, for example, H5D write calls, async calls, create the background threads with argobots, and then do the writes in the background. So you don't have to change a lot of, it won't be a lot of overhead, but it still will create background threads for the async operations. So the nice thing is that you don't need to launch or maintain any extra servers to do this. One thing that you have to keep in mind though is that if you have the option of copying the data to a buffer and then going on with your computation. So in that regards, you can overlap almost all your computation with IO. You just have to pay the price of copying that buffer to memory, so you're not overwriting what it's going to be written eventually. The other option is not copying that buffer, but then if you do that, you have to order your computation, so you're not overriding that buffer while you're doing your computation. So there's just some trade-off of if you do async. If you do Deos, you don't need the async vol because the Deos also handles async as part of its programming. So this is just how to use async. So there's a description here and a link how to use it. It's on GitHub. You can download both the async vol and you need argobots to run it. And then you can compile, you need to compile both the HDF5, the async, and then argobots. Then to use it, and we'll see this in an example. This is how you typically use vols, is you set the plugin path to the async vol, and then you have the HDF5 vol connector. That's usually what it's registered for HDF5, so HDF5 knows what it is. And then for explicit async, you'll introduce this event stack. So this keeps track of what events are completed. So for example, if you're doing a create the file name, this would be the synchronized version. If you want to do the async version, you stick on this event set stack ID. So that way you can track which events are how many events are still left to be completed if you want to monitor that. I won't discuss this async vol in detail as part of this hands-on. I just wanted to make you aware of that it's available if you choose to do async type of IO. So again, you have your async version. It's just, we have async calls now in HDF5, and then they just have an extra parameter with this event set, and you can control those event sets with, you create them, you can wait for events to finish, and then you can close them. You can also check for errors in the event set. And there's examples online, I think in our repo of how to have an example code of using async. Yeah, so this is just an example of how to do, you change your async code. So this is a synchronous file, and this is how you would change it to doing async. So you just add the parameter. You would add it, if you wanted to wait then for all the async to complete, you just call H5ES wait, And then for this case, it waits forever for all of them to complete before moving on, and you close it. So that's basically what you have to do to change your code to be able to use it. With that, I think I'm done. It's an overview.
Thank you, Scott. Is there any questions?
Yes, I have one question. Could you go back to that diagram that you have is like a circle with the different colors of data sets? I think it's 36 or something like that. Or yeah, or before. That, yes, could you repeat exactly? So how do we, what is this exactly? And then how do we get the different test cases to evaluate that you present in the rest of the slides?
Right. The code cycles through all these different parameters. So it's like there's 191 or 192 different sets of parameters around this circle, right? So each ray will be one that it cycles through, that this program cycles through. So if you look at this, so that was one, this is one of the rays that it cycled through.
Yes, but this is a particular program that you created?
Yes, it's you
And
can
how,
download it from here.
okay, and how do we pass this to the reality of our codes?
Well, I mean, it gives you an idea of how the system performance would be. So it's not maybe a one-to-one comparison between what your application would be, but it would give you an idea of what you probably shouldn't be doing in your application. So you probably shouldn't be creating, for example, 2D arrays and using chunk data sets and filling them and using certain alignment. So it kind of just shows you a way to, I guess, get an idea how things behave on that system itself. It's not definitely not going to be, if you do this, you're going to get the best performance. Although you have a good odds of, if you choose something similar to these down here in your application, you're probably going to get pretty good performance.
Yeah, but you show also difference between GPFS and Lustre. So is this gonna affect this
Yes.
graph too? So
Yeah, it will.
So this one was, do you remember if it was?
This was on
Lustre?
Polaris, so this was last year.
This is Polaris, okay.
Yeah. Yeah, and it also is not, if you look at some of the Polaris with subfiling, let me see, with subfiling, you can see that it starts off better with independent, but then it starts when you get to the higher collective. And I have a feeling if I ran more, that collective will probably start being better than independent, but it's hard to say. But sometimes it switches whether you should use independent, whether and how many ranks you're using. So it's still, it's kind of still trial and error.
Thank you so much.
Sorry, yeah, I have a question on sort of the thread safe HDF5 and parallel HDF5. Are these compatible? And do you have any general thoughts on using thread safe HDF5? You know, this is largely to sort of try to guard against if someone decides to read a small file while we're doing IO on a separate thread or something like this.
We haven't had a lot of experience people use it because we tell it's unsupported, so we don't have a lot of users doing that. I don't know. Jordan, do you have any experience with?
Not really. Yeah, typically the thread safe version is, you know, serial applications trying to use that, but for the longest time we've just documented them as being unsupported together. It would be an interesting use case for sure, though, especially since subfiling is starting to branch out a bit more into parallel plus MPI threads. It would be interesting to see for the library working in parallel with thread safety. But yeah, we haven't seen a whole lot of people doing things of that nature.
Okay, yeah, we've been sort of cautious about it because, you know, we get this warning that this is unsupported. So we're like, we'll just have to do locking and everything ourselves, which is okay. But
we changed that though. It's supported now. Thread safe plus parallel is supported in 1.13.2.
Oh, that's great. Okay.
I mean, there was no reason, we didn't change anything. There was just, it was one of those things that we never really carefully tested it, so we didn't want to turn that on, but there's no reason to not have that, so we changed that policy.
Okay, that's good. Yeah, so and then we'll probably play with using the thread safe variant.
If you do encounter problems, please let us know. But yeah, we don't.
Definitely. Okay. Yeah. Yeah, we don't hit it all the time, but so our application is sort of gravitational wave physics where you have both volume data and sort of surface data that you need to extract and write separately. And currently it just involves sort of quite a bit of file management since the data is being written independently and this sort of thing. And having the HDF5 library deal with it in a thread safe manner would just make our user side of things easier. So.
Yeah, that'll get pushed downstream as we release more versions of 110 and 112. But like I said, the only change that we made was to just tell configure and CMake that it's okay. So you can feel free to use enable unsupported in other versions too.
Okay, that's awesome. Thank you.
I think it still remains untested, right? We don't have any regression tests for that scenario, right?
Yes, we don't have any tests for it.
So
Yeah.
it's still uncertain.
Yeah, it's
whether,
still, but there's no theoretical reason that we could think of to not have that.
right. But there's no guarantee.
Because everything still uses the global lock, right? Like, doesn't matter which API call you go through parallel or serial, it still slams the door in every API.
Oh, right.
Yeah.
Okay, yeah. Right, so basically if I tried to write even to two separate files, that would be a locking operation.
Right, yeah, because it's not just file state, it's also like library state, right? And
Yeah.
weird things in the library, things like IDs and stuff like that, and those data structures are not thread safe. So it doesn't matter what you're doing on the file system, just creating IDs is not thread safe.
Are there any plans to try to make those aspects?
It's a big job. There's a company that's trying to do it. We'll see how that turns out. If it works out, it'll be something we'll incorporate into the library. But it's a big job, right? It's bolting thread safety onto a 25-year-old application that was not really designed to be like concurrent.
Yeah, no, I mean we also have 25-year-old MPI codes, and yeah, trying to make those thread safe, the easiest solution was, well, let's just not worry about it.
Yeah, global kernel lock, but we're trying to do that, and we're trying to adapt the library to be better about that in the future.
Okay, cool. And I also have a question about sort of this SWMR stuff and this sort of a thing. Is there a general recommended way if I just want to read, let's say we have a file that's dumping some L2 norm of some error quantity in the domain, and I can also use this sort of to track the progress of the simulation. Is there a good safe way I can just view the data? It currently, understandably crashes HDF5 if I read and look at the data at the same time, and write the data at the same time. Is there a general sort of recommendation for wanting to view?
Swimmer is not supported on parallel, so
okay.
I don't think there's a way of doing that. And even the new swimmer, like BFD swimmer, which isn't merged into the main development trunk yet, I don't think that is going to be supported on with parallel either for swimmer functionality.
Yeah, and even just swimmer itself doesn't actually solve our problem, because sometimes I think it's only like certain things that you can write at the same time as read, and so it doesn't.
The current version of swimmer only is for basically data set appends, right? It's not for, you can't create objects or do other things like that inside the file. It's limited to just that one use case. The newer version of swimmer, which hasn't been merged yet, is most things in the library.
Okay.
But those were all designed with serial in mind and not parallel.
Right. Yeah. No, everything gets very complicated as soon as you go parallel with anything. Okay.
Right.
Yeah, do you have any recommended workflow sort of on if I want to look at a file during the simulation, or is it just don't touch it? That's just the easiest way to deal with it.
I don't know, Jordan, Scott, like as far as I know, like I don't think that's that's really something you could do in HDF5.
No, you'd have to close it before you do anything and then reopen it if you wanted to.
Right.
Yeah.
Yeah,
So you-
no, that's fine. I just wanted to ask if, there's some magic flag somewhere that you guys know of.
No,
No,
Okay, thank you.
yeah, okay. So where are we at now in our agenda?
Oh,
So we have a break from 11:30 to 11:45, I believe.
Okay,
Correct.
I see a hands up though. Mark, do you have questions?
Yeah, I just wanted to continue the question I had previously. And so we saw that there's an initial offset of the data set at 2 kilobytes to 48 bytes. And I think that's because of the meta block size setting. The other thing I'm thinking about is the user block size with regard to alignment, since I think H5P alignment is relative to the beginning, the end of the user block. So I guess those factors need to be taken into account to get the IO performance that you saw from manipulating the environment, the alignment, sorry.
Mm. I mean, it should align it if you do all 0, it should align all the objects, so it shouldn't be affected by, you're saying that it does get affected by the metadata or the user block?
Well, I think there's two potential things. So there's a user block, right, which is this kind of space that the user can do anything with at the beginning of the file.
Mhm.
And I believe the alignment is relative to the end of the user block, which might make it different than the alignment that you perhaps want from the beginning of the file. And so that's one thing I could see could be a problem. And so I'm wondering if the IO performance is dependent on the alignment being relative to the beginning of the file as opposed to the end of the user block. The second is the meta block size, which can be independently manipulated. But I'm not quite sure how that interacts with alignment. And also what happens to the extra space that's skipped over due to alignment.
So in terms of the meta block size, at least, it's the smallest size of metadata blocks that the library is going to allocate. So it should be allocating them on the alignment boundaries. But the user block is an interesting question. And yes, since the alignment's relative to the end of it, I don't think we've tested with this, but I could definitely see that throwing off some of the alignment of the objects in the file. I think that'd be an interesting case to test for sure. But at least with as long as you set an alignment, I think the meta block size, whenever the library goes to allocate those metadata blocks, they should always be on the alignment value that you chose.
Right, thank you. I think maybe a workaround might be just setting a user block size to be the same as alignment size, and then everything should be aligned as you would expect. But
Yeah, that sounds reasonable. Yeah.
If there are no more questions, I suggest us to take the break now. And so since it's 11:35, it would be 11:50 to come back. So just be on the Zoom call, don't leave. We'll just be back in 11:50.
Thank you. If speakers could you make the slides available for review, maybe via the Slack channel?
Yeah.
Yeah,
Or
we
you-
can post those in the Slack.
Scott, do you want to stop sharing or do you want to keep sharing?
I guess we should start the demo.
Do you want to share your screen?
Yeah.
Okay. I know we checked that one, and now I'm thinking maybe you want to increase the font size a little bit. Or just
Increase
make
it.
Yeah.
Bigger, or is that better?
That's much better, yes.
Okay, so start the demo here. So I have HDF5 installed, the link in the directory that Kevin pointed out earlier. So here, I'll just post it in the chat. All right, I guess I can do that. Okay, so the HDF5 is, I downloaded it and installed it here. I added a build script if you want to build it yourself. So this is one, well, this is actually a feature branch, but essentially 1.13.2. I used the subfiling feature branch because I wanted to demo subfiling. But you can also just download 1.13.2 and build that and have all the features that you see here. Just so this is a script to build it on Polaris. It's pretty simple. I've also installed the log ball in the HDF5 directory, ball log based. And again, I have this, so I downloaded it, it's on GitHub. And I have the install script. So all you need is first install HDF5, and then you point the install script to where the HDF5 installed. So I've installed that as well. And then all the examples are in the EX directory. I have two examples here. So I have, this is the example. So it kind of goes along with what in the talk. So one writes essentially 9 data sets. The second example writes 9 data sets, except it makes it into a compound type and then writes it that way. So we kind of want to explore the difference between those two on Polaris. So if we look, sorry. So standard HDF5 parallel program. So you initialize MPI. And then I have options here if you just want to do writing or reading. And then you can switch between independent to collective by adding a -c argument. And then -n with some number of elements gives the size of the problem that is going to be the size of the data sets essentially. If you want to change that, default's pretty small. So then the first part writes the data set. So in this case, it has rank 0, create all the data sets, and it allocates it early. It just does fill time never. It uses the latest version of the library. It creates the file, creates the data sets, it loops through all the data sets since there's 9. So it creates, but doesn't fill anything. So it doesn't write any data. It closes it and closes the file. So there's a barrier for the other ranks to wait till 1 is done creating the file. Then it uses the Mpio file driver to open the file. So all the ranks will open it. all the ranks will get the the file space, and each rank essentially writes part of a hyperslab of each of those arrays. So here I just fill the data with some numbers, and then here I write each individual. So I open the data set that was created, and then I write it and then close it, and I do that for all the data sets. And then release all the resources, and then you can go ahead and reads the data back. So again, loads the Mpio driver, opens the files, creates the data space, and then each one will read part of that hyperslab of each data set, and then it will loop through all the data sets to opens it, reads it, and then closes it. And then I time the time it takes for both reading and writing it, and I close the resources. So it's pretty simple. And then the other one is the compound. So it's all similar to previous example, except now when I write the data, I create just one data set because I'm combining all the data sets into a single compound type. So I open a file with one process, create the file with one rank, create this data set, and then close it. And then again, I open the file with all the ranks, and then I fill the data. So this is the data. So each field then is one of the 9 variables. And I then write using one write that all those 9 variables as a compound data type, which is a file type. Then it goes and reads the data using that compound data type by just using the one H5D read. It's very similar to what the other one was. I have a make file for it. So it just uses the standard CC, as Kevin mentioned. It gives that warning, so you can ignore that. Now, if you look at the batch file, I essentially export the HDF5 directory where it's installed, and then I give it the LD library path. I can figure out how many ranks to use. Then I create I CD to a directory on the Lester system in Grand. I make a directory, and then I set the stripe size. For this case, I'm going to use 64 size and 16 megabyte stripe sizes. And then I set that for the directory. Then I CD into that directory. And I copy the executables to that directory. I'm going to run it. And here we'll go through various cases.
Scott,
Huh?
bring that back up.
Okay.
Sorry, just scroll up a bit.
Yeah, commented
Sorry,
on.
I just wanted to point out where it says CD at the beginning of the line there. This is the an old training space, so we want to substitute GPU hack for ALCF training.
Let me just do that now.
Also, while you're at it, I think the direct path for the one that you pasted in the Zoom is just HDF5. So there is a 5 missing that I pasted on the Zoom chat, but just to point out.
Okay.
And then I just wanted to reiterate this. Scott said this, but the way this script works, it's running out of this directory. So for example, you probably don't want to run out of Scott's directory. So, make your own directory instead of Brightonfeld, put your directory there. And then when you launch this, it's going to CD into this directory and run out of there. So just in case,
Right.
you can submit the script from anywhere, but it's going to run within this directory. Just so I just want to doubly point that out so that people don't get confused.
All right, so the first case is just running the defaults. So I do it old fashioned and I put all those commands on the line. For some reason, I couldn't get the bash script work. Maybe something's changed since then. Okay, whoops. Okay. Yeah, I'm using also probably a different, I'm using the old one, but so here I selected 8 nodes, give it a wall time of 60 seconds, and I scatter it and I use the count, and then I give it the batch, and that submits the job. I think it was an error, of course. So it gives an error.
Oh no, we do. I guess Nina, you did get a disk quota exceeded there.
Uh,
Let me just, I'll have someone double check our quota set before we get going.
should I use the other one for now for the demo? Maybe the GPU hack, because I think that one's all right for now. I'll just, so I can just go on with the. Okay.
Sorry, could you repeat, is there anything that we need to change in the build of HDF5? I'm getting a couple of errors, but I don't know if it's pointing to the ALCF training, and I copied it in a different location. So
Sorry,
the
did you make directory?
We need to build HDF5.
No, you can just link. You can just link to that HDF5. It's
Oh, okay. I
yeah.
thought you wanted us to build. Okay, we can just use. Thanks.
Mhm.
And what is different than the current modules that we have?
So one writes all 9 data sets separately. The second one, the compound, writes the compound, creates a compound type, and then writes all the 9 data sets as a compound type in one write. That's the difference between these two. It's still, I don't know why it's.
I think you have to edit the other line.
Oh, you probably don't have that directory. You probably have to make it. Sorry, I made you change that line, and then that ALCF training Breitenfeld doesn't exist. You probably
Oh,
have to.
yeah, you're right.
My apologies.
So you can see it's running in the system. And this is the job ID in this queue. And it's already done. Hopefully it worked. It didn't. Oh, okay. Okay, good, ran. So when it does a batch, it has this .e, which is if there's any errors, and then the .o is the output. So let's see if it's done, still running. So it ran on 512 ranks. Okay, so it completed. So the first case ran, so it did collective, didn't do collective or false. So this is writing all 9 data sets. So it took 9 seconds roughly to write the data, 1 second to read it back. If you're doing all 9, if you're doing a compound data type, it only took 6 seconds and then half the time to read it. So it kind of gives you an idea. I mean, it's not exactly qualitative, but or quantitative, but it gives you an idea of having bigger writes is better. So this is both, this is just using independent. So if we want to change it now to do collective instead. So this is added a -c to it. Let's just run that. So this is 89. So it's 9 and 6 seconds. So for this case, using collective took a little longer. So it took 12 seconds for the first case. And it was 9 before with independent. And 1 second. So it's much slower with collective for both reading and writing for this case size problem. Or if you use a compound type, it actually is still worse with collective for both reading and writing. So for this case, collective is not as, doesn't perform as well. So then if we go to let's try with the log ball. So in this case, all I did, so it's the same executable, but I set the plugin path, HDF5 plugin path, so that points to where the log ball is installed. So you point it to the lib where it is. And then you have to set the HDF5 all connector. So it's log for this case. And then this, the rest of this is how for HDF5. So this tells it to use the log connector instead. I'm going to rerun those 2 cases again and see what happens. So this is 92. So I have an alias for, this is what I'm using to get the stats, the status of the thing. So you can see that with the log vol, the write time is very good, 0.36 seconds compared to what was 9. The read time, that's one issue with the log vol is the read time cannot sometimes, since it's the way it writes it, the reading might be a little slower. So that's one trade-off with using the log-based vol. But the read time is very good for both. That was writing 9 data sets separately. And then if you look at writing it with a compound, it's basically the same as it was. So it kind of sees it kind of eliminates a lot of the variability you would see with, as we saw before, without the log-based vol. So that's kind of gives you an idea of what you can achieve with the log-based vol and how to use it. And if you were to look, let me see, if we go to, so the scratch directory where it actually ran is here. So here's they're actually HDF5 files, but they're in the log-based vol format. I mean, it's an HDF5 file, but they create, for example, pointers to different, where the offsets are for the different data sets. That's how they that's how they organize the data. So if you were to dump this, you would see their format. Let me see if I can see. Training. Alt. Oh, big font. Let's dump. We won't dump the data. So if you dump the file, let's see, HDF5 dump can see the log-based vol, but it has its own format. So the log-based vol will create a group log, and it'll write all those data sets as it sees fits. And then it creates supplement metadata type data sets that have pointers to the other data sets. So it's still an HDF5 file, it's just in the log-based file format. So let's go back to the last one and let's look at subfiling. Let's see. So the subfiling code is in this subfile directory, subf. And they're basically very similar. I'll just point out to highlight the difference between the two. So this is writing the 9 data sets. So it remains the same as the previous one. The only difference is instead of having the 0 process created, since right now, if you use subfiling, you can't have one rank create the data set using the subfile and then reopen it with all the other ranks. You have to have all the ranks opening that file, or creating a file. So I changed that to if subfile. So I set the environment variable subf to 1 if I want to do subfiling. Otherwise, it just uses the Mpio directory. So you have to include in your file the IO concentrator, this here. So we have the subfiling header and the IO concentrator header you have to include in your program if you want to use subfiling. And then I changed it so all the ranks are creating the data sets. Again, I have all the optimizations of fill time never. I also, let me see. I create the file and I create all the data sets, and all the ranks do that. And then if I want to optimize, I set the collective metadata. For subfiling, this doesn't seem to impact it very much. And then it's basically the same after that. There's no other changes in the code. If you look at the, I don't think there's anything, and there's the same changes were made for the compound one, where I just have all the ranks create the data sets and open create the file instead of just one. So now if we look at the batch, it's all the same, except now I want to try subfiling, so I just set the environment variable to use subfiling instead. And I also use the stripe size of 16 megabytes. And I also decrease the number of elements. So with subfiling, there's also a utility program. So this will run the program, and then there's a utility program to combine all the subfiles into a single HDF5 file. It's called Hdfi.sh. So that will combine all the subfiles into an HDF5 file, and then you can dump that HDF5 file with H5 dump as before. So let's run that with now subfiling. Let's see. Have to change. I'll just and I have the default of just creating one subfile per node for this case. Oh, I think I have to change. Oh, sorry, didn't make it. Okay, so it's running now with subfiling. Let's look at the output. Okay, so this is running with writing 9 data sets at once. It took 1.93 seconds to write all the data, and then to read them back all the subfiles 0.45, and then I ran the fuse program, and that outputs, that uses DD to put assemble the files back together into a single HDF5 file. I shouldn't print all those. Let's see here. It's still doing that. It does take a while to assemble the subfiles back. The idea is kind of do that in the background. So if you do a dump, and then you can do that time step, and then persist it to, if you want it as an HDF5 file, then to do that in the background in your program. So you don't have to wait for it to complete. Okay, it's all done. So let's go. Okay. So it got done fusing the files, the subfiles all together. It took almost a minute to do that. So it's a little slow. And I then used H5 dump on that file that it got, and you can see the 9 data sets, 4, 5, 6, 8, 9. That's from H5 dump. And if you were looking at the directory itself, this is so then it went on and ran the compound data type. So that for that, it took 1.63 seconds to write it, and then 0.33 seconds to read it. And if you look now, what you have in your directory, the subfile directory is, well, you have both, since it ran 2 programs, you have the compound. This is kind of this H5 in this case, it is just a filler to the, this isn't really an HDF5 file because it hasn't been fused back. This is just like a stub file for HDF5. So it has the super block. So if you have a program like Netcdf or CGNS that needs to read what the first 8 bits or 8 bytes of the file is to see what type it is, that it will still have that information in it, but it's really not an HDF5 file. And then you have your subfiles here, which is 1 through 16, because we ran on 16 nodes. And then the config file tells HDF5 the configuration, what subfiling used. For the first case where we didn't use compound, you can see that it put the files, and it's 19 gigabytes into this HDF5 file. So this is the actual HDF5 file that we dumped, but then you can see the 16 subfiles that it wrote for that case as well. So that's subfiling and how to use it on Polaris. I think that's the end of the demo for that I have. Is there any questions?
There were some questions with respect to running the scripts, if they need to do the hands-on. What is the project name? Shai mentioned is ALCF training, but I don't know if they mean something else. So Alfred, if you want to expand on your question.
It's okay. Maybe I'm a little bit a step ahead of Scott. Maybe he will tell us what to do when we have to do the hands-on.
Yeah, I can do that. I think we should maybe change the scripts in the actual, because that was my directory. We change them here, then maybe we can just copy the new updated ones to. So you should be able to just make it as that should work fine. Let's take the batch scripts. I need to modify that before the hands-on. I can do that. Let me see.
Yeah, please. Yeah, just update the batch.
The dash A. So the dash A should be ACLF training, right? Or the account. Yes. Yeah.
Correct.
Could someone copy and paste that command into Zoom or Slack?
Well, that's with A2. So you want to run less nodes. That might be a little overkill for it. And you might choose the should probably make the number of elements smaller, or else it's going to be a lot of people writing gigabytes worth of data. They have to be powers of 2. So I'll change that in the script. But if you want to change the number of elements to be smaller, it has to be power of 2.
So I think if people wants to talk, I mean, we have the kind of continuous hands-on, I think around 1:15 or so. We may not have the Darshan demo at this time, but I would like to give people yes, Kevin, did you want to say something?
I was going to say, I'll have something to show. Yes.
Okay. So I would say let's take the break right now. So we were supposed to get a 30 minutes lunch break. So it's 12:25. Let's come back at, I guess, 12:55, or let's just make it at 1. So let's come back at 1 p.m. Central, and then we can continue. I suggest people to stay online. You can send your questions either on Zoom or Slack. Slack have the continuation, so it might be a better place to do that. So let's come back at 1 p.m. Central Time.
And of course, if anyone wants to try the examples while we're on break, just post in Slack if you're having any difficulties, or let us know. So my recommendation is you copy Scott's EX directory over to your own space, either inside ALCF training or in your home. And then step one is to try to compile. And if you compile correctly, then you can take a look at the batch.sh and try to understand any components in there. And then, Scott, I don't know if you explained that basically you've got different types of test cases commented out.
Right, so if you want to uncomment it, just put the pound sign between. So this is a comment. So it starts at the double sign and then ends. So this, so you have to, so that's
Yeah, so
all
if-
commented out. Mhm.
Right, so if you go to the bottom of your file here, let's go all the way to the bottom. So right now, this is the test case he has uncommented. So if if you just ran the copy this over and ran it, you would be doing the test with the vol connector. But if you want, you can comment this out again and then go ahead and take one of the other test cases or whichever you like to test. And yeah, feel free to ask questions. It's always a bit of a challenge to get the script perfectly right so it can run for any person. So you might need to make directories or change a few of the paths. And no problem if you do, but if you're having trouble, just let us know.
I think Alfred is asking if he needs to just type make, or do we need to do an interactive session?
You can just type make.
Yeah,
You
you
don't
can
need to-
build at the login node. You don't need a compute node to build.
If you do have a GPU, you have to do it on a, you have to interactive, right? Or do you have to?
No, we have all the libraries installed on the login.
Okay.
The only case would be if your configure or build system was trying to do a runtime test and trying to launch a kernel, then of course
Oh.
it'll fail because the login does not have a GPU at this time. But otherwise, linking and compiling, definitely this code, no problem. You can do it on the login.
Yeah, since HDF5 doesn't use any of that, it doesn't need to, yeah, it doesn't run a GPU, so it should be fine.
And Scott, if you get a chance, it would be good if you could put your slides in the Slack channel.
For some reason, when I use that link on the invite, it gives me an error.
Okay, so that's because probably you were the user before, which I think you were, because we used ad test for the same channel, so your account is deactivated. So let me activate that. So that's actually another note. If you try the link and it doesn't work, just ping me on Zoom and I will activate your account. If you were a previous user, we remove them, but it doesn't tell you what's the problem. So that's kind of annoying, but I can fix it.
Yeah, I think you only have to change that one line in the batch to CD to wherever you want to run the examples in.
So Scott, I just activated your account, so you should be able to click on the link and join.
Okay.
Thank you.
still is not working.
All right, let me see. I activated you, so I should be able to just add you. They added you to the channel. But you are not online, you're offline.
It's the, let me see, it's the join Slack.
No, I already added you. You were in the channel, so you just have to get to the workspace. Or do you want the link for it? It's ALCF-workshops at Slack. Let me see if I can share the link somehow with you. Yep, okay. ALCF-workshops. So look for this ALCF-workshops space. Let's see if I can send you the link. So if you click on the link, it doesn't work. I mean, you're already in the channel.
I don't see the channel would be on the web, or is that, I don't
Is
see the
this
channel in my Slack app.
okay? So
Maybe I'll add a channel and see. Let me see.
copy.
If you don't have the ALCF workshops Slack, you need to then just hit the plus button. And in theory, it'll find any workspaces that you don't currently have added and ask you if you want to add them.
What's the archives? Were you able to find it?
No, it didn't show me.
Right, so yeah. Hi, Kevin. Do you want to, are you going to present some info about Darshan?
Yep.
Okay.
We ready to start?
I mean, the morning we have 30 people join, so we can wait a couple of minutes, I guess. But if you want to share your slides, you can do so.
Okay. Also to reiterate, if you're having issues running or building, please let us know. We'll try to sort it out after. This will be a short presentation, so we can help work with you to get your code running or building if there's any problems.
Yeah, I ping people on the Slack channel, so hopefully more people can join us. I think it's okay to start.
Okay. All right. So I will put this notes into the Slack as soon as I'm done. But I want to walk through this. Unfortunately, it's going to take some switching back and forth between different shares. So we'll just kind of walk through this step by step. So I don't have a lot of, I'll just give you a general concept of what Darshan does. If you're not interested in it, that's fine. But if you are, there's plenty of training materials to find out more about Darshan. But it's sort of like a statistical profiling system. It is not a tracer. It will capture some information of IO about your job in a very lightweight fashion. So it typically has a runtime overhead of less than 2%, which when you run, you can just turn this on. It will collect data. Then you can load the log after the job finishes and see what your IO happened during your job. This is great if you're not so familiar. Like if you already know exactly what your job does for IO, you might not need this. But if you're like, I don't exactly know the IO portion of this code, let me see how it's behaving. This would be a great tool to do that. So let me walk you through how we use it, and then I'll show you the results at the end, and then that'll give you a better idea what kind of information you can see. So in your submission script, so if we just take Scott's batch.sh, we need to do two things. First, we need to, I suggest defining a variable called Darshan preload, which then points to this dynamic library. This also assumes you're using C. If you're using Fortran, we need to add one more library. So let me know if you need the Fortran. But I don't, then we're going to use this and set LD preload. I don't recommend setting this directly in LD preload because in everything you do in your script, we'll be trying to load this. We've generally tried to harden it so it doesn't crash like, LS or something. But my recommendation is set of some variable like this. Then to the MPI exec line, you just add -env, set LD preload, and then Darshan preload. Now, whatever binary you run will load this library first, and Darshan will intercept IO calls to record information about it. For the purposes of this demo, I also suggest setting one more environment variable, and this is called Darshan log file. You're setting this to the exact name of the log file that will be created. So here it'll be called test.darshan. You can name, by convention, we call the .darshan, but you can name this whatever you want. This will be created at essentially in the current working directory of the job, since we've given no relative path or absolute path. But you could give a different path here if you wanted the log file to land in a certain place. So I'm going to switch over and show you my batch.sh so you can get a better idea of how that works. Okay, I'm sharing my terminal. Is this readable, or I need to make the font bigger?
No, this is too small, Kevin.
How's that?
It's better.
Okay. All right, so we can see at this point in the file here, I've just created this export variable, set this to the path to this dynamic library. Everyone should have access to this. It's in the LCF training project. Then, oh, sorry, I've got this set twice there. That's all right. Then for your MPI exec, whichever MPI exec you want to profile, like I said, just add the NV LD preload equals $darshan preload, and then -env darshan log file. Again, any name you want. I just called it test.darshan, and then the rest of your parameters. In this case, this is profiling just this one invocation of example. The next one, example CMPD, that one's darshan log won't be created. If you did want to create a log for both of these, put these variables and then make sure you put a different name for your log file. So if this were test1.darshan, the next one, you couldn't call it test2.darshan. Otherwise, it won't, I believe it won't overwrite the file, and it just won't create one. So here I'm just instrumenting this one. So once you've done that, let me rescale this a bit. Okay, can you see the very bottom of the screen here? So you're going to submit the job and it's going to run. And then whichever directory you set to be the base directory. So I'm using another project that I have. I just created this directory, HDF5 Workshop. So in Scott's script, it creates a subdirectory with the job ID. So, and inside that directory, so here is where all the output files of the job are going. So this is the working directory of the job. And as Scott said, he copies over the binaries. And we see when we ran, we got a single log called test.darshan. So now let me switch back to my slide for a second. All right, so as I said, you run the test case, then look for the output directory. So this is a directory that you specified inside the batch.sh at the top where it does the CD. So if you kept it as less grand projects ALCF training, you might have made some intermediate directory. And then, like I said, this script creates another directory named by the job ID. So assuming we don't run another few hundred jobs, it'll be 32 with some number .polaris. And if you CD into this directory, you'll find test.darshan. Now, in order to view the results, there's two ways, and we can start with at your command line, export the path, and then add the path here, LCF training darshan 340 bin. This will give you access to the existing binaries. Also set this LD library path. This is make sure we load the correct darshan util. So again, this just points to the lib directory. So once you set these things, you should be able to find darshan parser in your path. And you can type darshan parser test.darshan. This is a ASCII output, so it will start dumping to your screen. So you can pipe it through less and take a look at it. And this is at the lowest level. It gives you all the counter information. This is like the most detailed way to view the data, but requires you to have the most knowledge or look for something very specific. The next method is to use Python summary. This is something new we've been working on, so it's a little bit rough around the edges, but you can install this yourself with this command, pip3 install. -- user says make the installs local to yourself. So put Darshan and then these two other libraries, which are not included in our default installation, but are needed. Those three will be installed. You can then, again, for your test called Python3-m Darshan summary, and then give it the Darshan log. So in my case, test.darshan. And this will generate a test report.html. Once you have this file generated, then SCP this back to your desktop or your laptop, and then you can view it. So again, let me switch my share. Okay, so
Kevin, I think a couple of people were mentioning that the font is too small for them, so maybe you want to.
oh, okay, on the here. How's that?
It's good for me, but Mark and Alfred that were complaining about font, please let me know if it's okay or not.
Yeah, it's very hard for me to tell what size is
Yeah.
acceptable.
Yeah, I think a little bit bigger might be okay. The problem is if I'm viewing this like it's smaller than my full screen, then it's really hard to read. And then, okay, yeah, that's good.
Okay,
Yeah, for people who are looking at it from the laptop, it'd be too small unless you have a really large terminal.
okay. Is it readable now, or you still need the font bigger?
Yeah, it's better. Thanks.
Okay. So we can type Darshan parser. It should be found in our, and then give the log file. And like I said, I suggest piping it through less. I can't see this myself. All right, so when you do that, this is all going to just be ASCII output. So the header here is some information about the log and when it was generated, who generated it, so on and so forth. Then these are the type of data that's included in the log file. So each of these modules contain different types of data. So the ones maybe we'll look at this will be easier to read in another format that I'll show you, but there's two modules that cover HDF5, the file data and then the data set data. This is a list of mount points, which these can be referenced then in the down further, it'll reference where this file was stored to. Fortunately, on modern systems, there are a lot more mount points. This at the top header is a little bit of documentation, so you could read this to try to understand the counters. Hopefully, it's somewhat clear, but I'll just take you through one. So for here, the counter name is in this column under counter. So for example, this is the number of opens. This here, rank -1, means it was opened by all ranks. Now, this test case was a single node 32 rank run. So all ranks open this file. That's what -1 means. This is just a hash of the file name. So this the record ID. So anything that's done with this file is tracked here. And then this is the file name. Then here is the mount point and then the file system type. So for each different file that's operated on, it will be opened or closed. You can see all the metrics. So for example, if, a lot of things might be opening up some or trying to open various files that are not important. If you know the file name, or you can find which file is interesting. So let's look for the output file. Okay, here we are, H5. So again, there's a lot of counters. These are us all POSIX. Then there's Mpio counters. Again, the counter names are in the center here. And so depending on the counter, it also depends on what this means. So again, these are mostly integer counters, so they're just counting the number. But there might also be like counters like this, which is the number of bytes. Usually it's fairly obvious from the name what type of data is captured in there, whether it's an integer count, a byte or byte offset, or there's also some time, which are the floating point values here. So these are in seconds. So again, this is the finest grained way to look at this data, perhaps not the easiest. But if you're searching for something very specific, you can just pipe that through grep and you'll find it. So let me show you the generated report.
You said that was run on 32 ranks, or I mean,
Correct. Yeah, one node with 32 ranks.
but it shows 64 opens, which is
Oh, also, I guess I should double check. I think I ran this again a second time. So I believe this sample I have is from 32 processes. So I could be wrong for that log because I wasn't paying that close attention. All right. But it's at the top of the, I'll just double check while I'm sharing this other thing. Yeah, it was 32 processes. So how is I assume these is quite small. What I'm sharing. Like, is this text at all readable?
no, it's possible.
Yeah. So let me, I'll talk through this and I'll zoom in as we go. So this is the other way. If you use a Python script, you can generate this report. All of the graphics and stuff are embedded in the HTML. So when you just copy it back to your laptop, desktop, just open up with any browser, all of the data is contained within the HTML file. So you'll see the summary. Here's 32 processes. It'll tell you what was run. So this was the example test with, I don't remember. This was the number of elements. Is that correct, Scott?
Yeah, that's correct. Mhm.
Yeah. And then again, here's the similar, this is the data that was captured. So for example, we can see that we have HDF5 data captured in here. Okay. So the first thing, there's this heat map. So a lot of this data won't be super interesting for these trivial benchmarks, but you can get an idea of just what's here. So this is intended to be a summary. So let me blow up one of these. Is that somewhat readable?
Yeah, it's readable.
So this shows the intensity of data over time, and you can kind of see that it's relatively well balanced, which is, you know, since it's generally just doing IO, that's all what this job does. And then again, this is, I believe, the total aggregate IO for the whole rank, and they're all even. This is the data intensity, so you can see how much data is written over time. So this just gives you a general overview of the IO intensity that occurred in the job. And again, in this case, these graphs won't be super interesting because of the benchmark. This next one, Scott kind of mentioned in one of his test examples. This is looking at the total runtime with all the modules. So as Scott said, the ideal case should be the HDF time is identical to the Mpio time, which is identical to POSIX, because the implementation of Romeo is such that HDF5 calls Mpio, which calls POSIX as implementation. So if these are all the same time, that's good. There's no loss. So then we see in the HDF5, there's just a bit of extra time for the metadata. But if for some reason, this again, if you were doing either you had a mix, so you have some HDF5 IO mixed in with some POSIX IO, right? Then you might get more variance because not everything is the same. But for example, if you saw your Mpio time was very large, but your POSIX time was small, that means there's a lot of communication overhead in whatever collective or operation you're doing, which may or may not be a good sign. Usually it's not a good sign if you've got a lot of communication time spent with little IO time spent. So that's one thing you can see in this graph. So let me For each of these are the same. So let me kind of jump down to the HDF5 one. So here we can see some specifics for HDF5. So I believe this is 512 meg, which was what was being written, and then how many times it was written. And so we saw all accesses were done here. Again, like I said, this is still a work in progress. So these are counts for each bar, but they're overlapping. But they're 280 something for these two bars. You just see that all IO is done in the singular bin. If we can see up here, if I go up to the POSIX, we have some of these small IOs which are occurring. That's likely coming from various metadata operations HDF5 has to do internally. So they aren't necessarily calls you're making directly to do this writes. And then you can see a breakdown by operation. So again, just how many times they were called during the course of the entire program. And then just stdio is for basically if you're doing reads or writes of like standard output, standard error. So generally you don't need to ignore this unless you're specifically using standard in and standard out to do your IO. Then this last graphic is just, it's mainly important if like we wrote any data to home, we would see a breakdown for home, or to some other file system. We'd see that breakdown here, and that can be an indicator if you're potentially writing data. Like if you wrote all your data to home, your performance was bad, well, that might be why you should have been using one of the high performance file systems. So that's kind of an overview of what you can do. So for any of the test examples that Scott made, you can instrument those with this. I specifically installed this one in the ALCF training because it matches, it's built against the version of HDF5 that Scott built. And so they're both working with 1.13. So that's kind of my brief overview of kind of doing some initial performance gathering for your IO.